This video is going to start our work on sections 5.5 and 5.6. In recent modules, we've been working towards understanding the distribution of the sample mean, and we're also going to start talking about the sample variance today. And these distributions are going to be the basis of the methods that we use in our inferential statistics that we have probably seen in other courses, making confidence intervals and doing hypothesis tests, and using data from a sample in general to draw conclusions about what's true in the population. So previously in our other modules we defined the sample mean. If you remember the sample mean, we have the notation x bar, and we calculate it by taking 1 over n times the sum of the xi, where n is the sample size. So we're just adding up all of the observations in our random sample and dividing by the size of the sample. We also learned how to find the mean and the variance of the sample mean. The mean of the sample mean, I'll use the notation mu of x bar, is the same as the mean mu in the population that we're sampling from. And the variance of x bar is sigma squared over n, where sigma squared is the variance in the population that we're sampling from. And we also saw that we had something called the standard error. Sigma of x bar is the standard error, which is equal to the square root of the variance, so sigma over the square root of n. So we've kind of worked on those pieces already. Now in this lesson what we're going to do is we're going to fully describe the distribution of the sample mean when we're sampling from a normal population. We're also going to learn about the central limit theorem and how it's relevant to making statistical inference. We'll, in the second video that accompanies this lesson, learn about the sample variance by defining it, looking at distribution of the sample variance, and learning about another distribution that's important for inferential statistics, which is called the t-distribution. So that's where we're headed. Okay, so we'll start with a theorem about linear combinations of independent normal random variables. So if we have x1, x2 up through xn, they are mutually independent normal random variables. They don't have to have the same mean. They have means mu1, mu2, and so on up to mu sub n. And variance is sigma squared sub 1, sigma squared sub 2, up to sigma squared sub n. So again, they don't have to have equal variances. Then the linear combination that we make by taking each of those random variables and multiplying it by some constant, and then adding that up to make a linear combination, is going to have a normal distribution also. We can find the mean of that normal distribution by taking the sum of those constants times the means themselves, and the variance by taking the constants squared times the variances and adding those all up. So that tells us about, as I say, how to find the distribution of a sum of independent normal random variables or any linear combination of them. So first of all, let's see how we can use this theorem. Suppose that adult women in the United States, height follows a normal distribution with a mean of 65 inches and a standard deviation of 3.5 inches. And that among adult men in the United States, height follows a normal distribution with a mean of 71 inches and a standard deviation of 3 inches. Suppose that I randomly select one woman in the United States and I randomly select one man in the United States. I can use this theorem to answer questions like this. What is the probability that the sum of their heights is more than 140 inches? Now, the way I'm going to think about this is that I know if I call W the height of the woman, I know that that's randomly selected from a normal distribution with a mean of 65 and a variance of 3.5 squared. I also know that the man's height was taken from a normal distribution with a mean of 71 and a variance of 3 squared. What this theorem tells me is that if I'm interested in the sum of their heights, W plus M, well then it's going to be a normal distribution also. The mean is going to be the sum of the two means, so 65 plus 71. The variance is going to be the sum of these two variances, 3.5 squared plus 3 squared. So that means that the sum, W plus M, has a normal distribution with a mean of 136 and a variance of 21.25. Now if I want to know the probability that that sum is more than 140 inches, I can standardize, say, okay, well that's the same as the probability that a standard normal random variable would be more than 140 minus the mean of this distribution divided by the standard deviation of this distribution, so that's the square root of 21.25, because we have the variance here, which is the probability that a standard normal, Z, is greater than 0.8677. And then using either my normal CDF or a table, I can find that this is equal to 0.1928. So that would be how I can think about finding probabilities that the sum take on a particular value. I can also use this theorem if I want to think about what is the probability that the randomly selected woman is taller than the randomly selected man. The reason that this can be solved with this problem is because if the woman's height is greater than the men's height, then the difference between their heights, the woman's height minus the man's height, has to be greater than 0. And so I can think about the distribution of the difference in the heights. It's my W and my M. Now, this is also going to be a linear combination. We can think this is sort of like my 1 times the woman's height plus minus 1 times the man's height. So this is going to have a normal distribution. The mean of the distribution is going to be the difference in the two means, 65 minus 71. The variance is going to be the variance here plus negative 1 squared is 1 times the variance here. So again, my variance of the difference is going to be 3.5 squared plus 3 squared, which means that this distribution is normal with a mean of negative 6 and a variance of 21.25. So now at this point I can use this to find the probability that the woman's height is greater than the man's height, which is the probability that the difference in their heights is greater than 0, which is the probability that a standard normal, if I sort of, is going to be greater than 0 minus the mean of this distribution of the difference, minus negative 6, divided by the standard deviation, which is the square root of this variance, which is the probability that my standard normal random variable is greater than 1.3016, which gives me 0.0965. And again, I would find this using either a table or some sort of technology like my calculator to find the area under the normal curve. So a couple of applications of this theorem. Next, we're going to look at a corollary of that theorem. The corollary of this theorem tells us that if we have x1, x2, up to xn, observations from a random sample of size n, taken from a normal distribution with common mean mu and variance sigma squared. Then the sample mean, it has a normal distribution, and the mean of that distribution is going to be at the population mean mu, and the variance is going to be sigma squared over the sample size n. So we'll use this then to answer other types of questions. Suppose that among adult women in the United States, height follows a normal distribution with a mean 65 inches and standard deviation 3.5 inches. Suppose I randomly select a sample of 10 women in the United States. What is the probability that the mean height in the sample is within 1 inch of the population mean? So now I'm thinking about the sample mean. I know that it's going to have a normal distribution with a mean that's the same as the population mean, and that is a population mean of 65. And it's going to have a variance that's going to be equal to the population variance, 3.5 squared over n, and n here is 10. So that means that the sample mean would have a normal distribution with a mean of 65 and a variance of 1.225. Now, I want to know the probability that the height in the sample, the mean height in the sample, is within 1 inch of the population mean. So being within 1 inch of the population mean would mean that my sample mean is somewhere between 64 and 66. So I'm looking for the probability of that event. Again, I'm going to standardize using this distribution. This is the probability that 64 minus the mean of this distribution, 65, divided by the variance of this the standard deviation of this distribution, square root of the variance, 1.225, is less than or equal to a z, standard normal random variable, is less than or equal to, I'm going to standardize again, 66 minus the mean of the distribution of the sample mean, which is 65, divided by this standard deviation of this distribution, square root of 1.225. So it's the probability that a random variable takes on a value between negative 0.9035 and positive 0.9035. And again, I can use my calculator or a table to find that area under the curve between those values, and it comes out to be 0.6337. So there's our solution. So this is telling us about the distribution of the sample mean when we're sampling from a normal population. We're also going to talk about the central limit theorem. The central limit theorem is the topic of section 5.6, and it is stated without proof because the proof of the central limit theorem is quite complicated, and we really don't have all of the theoretical machinery to prove it. But the central limit theorem tells us that if we take a sample of size n from a distribution, any type of distribution, doesn't have to be normal now, with a finite mean mu and a finite variance sigma squared, and as long as the sample size is large enough, then the sample mean x bar follows an approximately normal distribution. The mean of that distribution is at the population mean mu, and the variance is the population variance divided by n. So essentially what we're doing here is we're just saying that our statement that we made here in our corollary is in fact true no matter what type of population we're sampling from, as long as the sample size is big enough. So we can use this to find approximate probabilities by approximating the distribution of the sample mean with a normal distribution. And that approximation will be better the larger our sample size is. If our sample size is very small, it's probably not a very good approximation unless we're sampling from a normal population. If we have a large sample size, then it's probably a very good approximation. All right, let's solve a problem. So suppose that xi denotes the waiting time in minutes for the ith customer, and that has an exponential distribution. An assistant manager claims that the mean waiting time, mu, for the entire population of customers is 2 minutes, and the manager doesn't believe that claim. So he observes a random sample of 36 customers and finds that the average waiting time is 3.2 minutes. We want to decide whether the manager should reject the assistant's claim and fire him. That might be a little drastic over this kind of a mistake. But, okay, so let's look at it. So what we're going to be thinking about in this situation is we're thinking about, okay, so what if the assistant manager's claim was true? Would we expect to see a sample like this one, or would this type of a sample result be so inconsistent with the assistant manager's claim that I don't believe it? Right? So we'll start by saying, okay, suppose for a minute that the claim is true. If the claim is true, then the mean waiting time, which remember for an exponential distribution, our parameter theta is the mean, would be equal to 2. And in order to use the central limit theorem, we also need to know what the population variance would be. But in an exponential distribution, the variance is just our theta squared, and we just figured out that theta is equal to 2, so the variance would have to be 4 in that situation. So if the claim is true, then our sample mean would have an approximately normal distribution with a mean the same as the population mean, 2, and a variance that would be our population variance, 4, divided by n, which is 36 here. So now let's say, okay, so if this is true, what would be the probability of seeing a sample mean that was as big as the one we saw here? Well, let's see. I can standardize based on this distribution. That'd be the probability that a standard normal random variable takes a value greater than 3.2 minus this mean, 2, divided by the standard deviation of this distribution. Here we have the variance, so that would be the square root of 4 over 36, which is the same as the probability that our standard normal random variable would take a value greater than or equal to 3.6. Now, if we use our table or the calculator to find this probability, it comes out to be about 0.00016. So what this means is that if the assistant manager's claim were true and the average waiting time between customers is 2 minutes, the chance of seeing a sample like this one or something with a longer average waiting time is only 0.00016. Right? So that would be extremely unlikely to have happened if the manager's claim were correct, the assistant manager's claim were correct. So I would say that the manager has strong reason to doubt that claim. Because if it were true that the average wait time were 2 minutes, there's almost no chance he would have seen a sample mean like his. And just to sort of make a note, this is an example of hypothesis testing. in your introductory statistics courses where you have seen hypothesis testing previously, this is really the process. We formulate a claim which we're trying to decide if we have evidence to reject. That would be what we'd call normally our null hypothesis, because the mean is equal to 2. And then we find a p-value, which would be the probability of seeing our sample statistic, or something more sort of more extreme, farther from our hypothesis. And if that chance of seeing sample data like ours, if the null hypothesis were true, is small enough, we reject it. So this is kind of the process of hypothesis testing. And this is why the central limit theorem is so important. It's because all of inferential statistics hinges on understanding the distribution of the sample statistic. And so making inferences about means, and in fact also about many other sample statistics, is based on the central limit theorem. And that will be the end of our first video. We'll pick up with video 2 in a minute.